Hello everybody, welcome to the Lab 5 demo. This is the PID control experiment, and in my experience this is the most fun lab of the class because you actually get to see a controller working and it's pretty easy to do and the results are good. So in this lab we tune a PID controller by two tuning room methods. The first one is Ziegler-Nichols auto tuning, popularly known as ZN tuning, and the other one is Cohen-Kuhn tuning. Okay, so here's what we want to do in this lab. This is going to be this is the part when you have the controller. I explained that so you can understand why we do the other stuff. So this is the output to the motor, that is the input from the encoder, convert it to an angle, and then you get the error, pass it through the gains Kp, Ki, Kd, one integrated, one differentiator. That's a pretty standard PID control loop. Add them together, keep the control output to the motor. Okay. Now the question is, how do we get the numbers Kp, Ki, and Kd? There are ways to do it. The first one we see is Ziegler-Nichols auto tuning. For that, we have to make this block diagram here. This is going to be the encoder input, the motor input from your encoder. Convert it to an angle, give it to a relay, and the relay goes to the analog output, the same block that's up here. The relay settings need to be tweaked, giving it a on and off point of, say, +1 and -1 can be the on and off values, and the on and off points can be +0.1 and -0.1. When you double click on the relay and open the dialog, as my friend will show you, you can see the values. Well, to most of you it might occur, however does this circuit or this block diagram even start working? The relay has a default initial value, and that goes to the motor. When the output of the motor switches below a threshold, the relay gets a different signal which sends a different output. That's how it operates and sends out a square wave. So this is how the square wave is how your relay output is going to look like, and something like the sine wave is going to be your motor's output. Let's call the amplitude of your output, not the peak to peak, but only from 0. Let that be A. Let the peak to peak amplitude of your relay input be 2 times H, so half of it is H. Once you have the A and the H, then you calculate the critical period, which is PU, which is the time for one cycle of operation. Once you have that, then you calculate one parameter called the KCU, or the critical gain, which is given by 4H times pi of A, which is the formula right down here. Once you have this, you will need to go to the Mechatronics class website, which you can find from the USU site, or search for USU Mechatronics, the 5320 class. Download the slides for PID control, which I remember is under week 13 of the class. Once you have that, look up relay auto tuning in that, and there is a table for relay auto tuning rules. Now, do not mix it with the step response tuning rules of Ziegler-Nichols. There are two versions. One is the step response, one is the auto tuning. Use the auto tuning one for the ZN rules and get 3 parameters. First one is called TI, second one TD, and the third one is KP. Now remember that KI is 1 over TI and KD equals TD. Once you have those gains, then you just go ahead, put it into this block diagram, run it, and see if your controller controls the position. One thing to note though, when you calculate the error, the feedback should be negative, but some of the motors here have their encoders flipped, so that has to be a positive. Otherwise you would give it a positive feedback and your controller would never control anything. The next method here is called the Cohen-Kuhn tuning. For this, we first make a model in plain Simulink, no WinCon involved. You need the K and tau of the motor you are controlling. Give it a step, close the feedback loop, record the output Y and the derivative Y dash. Here's why we do that. You make a plot of Y against time, which is this nice step response curve, and then you plot a maximum slope tangent to it. Okay, this curve is called the reaction curve. Note that this is a tangent not at the point at where the maximum slope happens. This is a tangent to that curve with the maximum slope. So The maximum slope is obviously going to happen at some point around here where y dash peaks, which is what you have to get. Then you have to write code to draw this line in MATLAB so you can calculate the other parameters. As we can see, T2 is the time when this maximum slope line cuts your steady state value of the response. T0 is the time when your output is either the first time when it is greater than 0 or the last time when it is 0, one of those. T1 is when this maximum slope line cuts the x-axis. Okay. Now for some of you, T1 and T0 can coincide. If that happens, it is bad. Some of you may even get T1 to be after T0. That's bad too. If that happens, you can shift T0 back by a very small amount, because in practice those two differ by a very small amount, so shifting them back, like shifting T0 back by 2 or 3 samples, doesn't really cause a lot of difference. The reason T1 and T0 cannot be the same is, if you look at here, we have got a bunch of formula calculating K0 and tau 0. Okay, so K0 is YF minus Y0 divided by step final minus step 0. YF is the steady state value, Y0 is obviously 0. The final value of your step input is 1, and the final value of the step output is obviously 0. T0 is T1 minus T0. So tau 0 is T1 minus T0, sorry. So if T1 and T0 are equal, this will be 0, and V0 is T2 minus T1. And then, using these formula, you have to calculate the gains. Now, the parameter tau 0 goes in the denominator of one of the formulas that you use for calculating KPK and KD. And that's why if tau 0 is 0, you will run into huge problems, because that will give you infinite gain. So no matter how small a tau 0 you get, it should never be 0. So do this part carefully. Once you have this, again, go to the slides that you downloaded from the Mechatronics class, look up Cohen-Kuhn tuning, go to the table, plug in these numbers in the formulas over there, and get the gains. Note that in the Cohen-Kuhn tuning, they use Kp, Tr, and Td. It's the same as Zn, except Ti is now called Tr, and so here Ki would be 1 over Tr, and Kd would be Td, and Kp would obviously be the same. After this is pretty much the explanation. After this, you just use the gains, run them, and see how your controller controls the position, and compare the two, which one's good, which one's bad. And my friend Amin here is going to demonstrate you exactly how that's done.
Hello everyone. Okay, for the first method, CN tuning, so this is the plot that we have to make. This is the relay. Let me show you the relay inside. For this demo, we're gonna use the on point and off point is gonna be plus 0.1 and minus 0.1, and for the output when on and output when off is gonna be plus 2 and minus 2.